Hello. Now this is well, on this course I'm doing the old course. This is on there. Okay, it's on the A2 course, but in the new linear spec, it's on the AS course, and it's all to do with momentum. Okay. Now some of this you will have done at GCSE. Really, all we're doing is building on from it. Okay. So you should know that momentum is equal to mass times velocity. Okay, so therefore you might get asked, what are the units of momentum, or there might be a question where you have to pick out the right units of momentum. Well, you know, mass is measured in kilograms, velocity is in meters per second. Okay, so therefore it's kilograms times meter per second. Okay, in other words, it's kilogram meters per second. Okay, so they're the units of momentum. Okay, right. So that's very basic knowledge. Now the next thing is more kind of a definition thing, really. Okay, so they may say something called impulse, and you go, what the hell is an impulse? An impulse is simply the change in momentum. In other words, it's the momentum after, take the momentum before. So it's the momentum after a collision or whatever you might be observing, okay, minus the momentum that was of the total system before the collision, momentum before. Okay, and so this would only work, okay, we'd only give you a non-zero answer in a couple of conditions. Okay, in other words, you'd only get a positive answer or a negative answer, okay, in certain conditions. If there was an outside force acting on the system, or if you're just looking at one object in particular. Okay, so that leads us on to something we call the conservation of momentum, okay, which is something you need to be aware of. The conservation of momentum simply says when there's no outside, see, it says momentum will always be conserved in a system. And I go, what the hell is a system? A system is just, it's not a computer or something like that, it's just two objects, okay, that you consider the total momentum before they collide and the total momentum after they collide, for example. I don't know why I attempted to draw that, it's pointless, but you get the idea, okay, or maybe you don't, but I don't really care. Okay, so that's critical to understand what the conservation of momentum says, okay? And it says outside forces, so basically if you were pushing this, okay, with a certain force before they collided, and then when they collided you remove this force altogether, okay? In other words, you would not be conserving momentum because you were given this extra momentum that it doesn't have afterwards, okay? So, you know, or in other words, I think a better explanation is if you said, okay, we're going to consider the momentum of this object and this object before they collide, but after they collide, we're only going to look at the momentum of this object. Well, you've discounted the momentum of that object, so therefore you've discounted conservation momentum. Momentum won't be conserved because you're looking at two objects before and then one object afterwards. Okay, so clearly it's not going to be the same. Okay, so momentum will always be conserved, but there's one thing that isn't necessarily conserved, and there's two definitions we have for it, okay? It's either what we class as an elastic collision or something we class as an inelastic collision, okay? Now they're to do with kinetic energy, and one conserves it and one says it is not conserved. Okay, so elastic, okay, and inelastic. Inelastic is where it is not conserved, where it is not conserved, okay? So, is not. You could think IN and it said in elastic, this is not in elastic. Maybe it works, maybe it doesn't, okay? So it is not conserved, so kinetic energy is not conserved, okay? Okay, so the total kinetic energy before the collide and the total kinetic energy afterwards is not the same. However, in a elastic collision, obviously, remember one, the other is the opposite. Kinetic energy is conserved, or there is no loss of kinetic energy. Okay, now we can further define this inelastic business, okay, because there's something that we call where we have a totally inelastic collision. Now that's not just me trying to sound cool today with today's youth. No, there's a situation where that occurs, obviously. Okay, now if we go back to the idea of we having them two objects which collide, I was going to say vehicle, car, but my drawing wasn't even close to that, so I'll just call it a thing. Okay, you could call me a thing on that basis. Obviously I'm not meant to be a car, but principle applies. Okay, so if we have two objects which, again, crap, they both collide, okay? Yeah, this isn't going well, but you get the idea, okay? So if they collide, and then after the collision, okay, they are moving together, either these, meant to be a car, you get the idea. If they're moving together after the collision, we call it a totally inelastic collision. And quite clearly, you could calculate a situation, just come up with a situation where before they're moving at two different velocities, and then afterwards moving at the same velocity, kinetic energy will not be conserved. Now, I've just given you a bit of an insight into how to calculate something like this. Okay, so say this is, we'll call this mass 1, okay, and this mass 2, okay. And initially, this mass 1 has a velocity u1, a given velocity. This mass m2 has its own initial velocity, which we'll call u2. Okay, not the same, just a letter. Okay, this just represents, just like x does, it just represents a number. Okay, so they're moving at two different velocities. Now, I've drawn them coming together. You might want to just draw them m1 catching up m2 and pushing it along. Okay. And then afterwards, they both have the same velocity, okay, which we'll call a final velocity of v, okay. So, if it asked you to calculate the n velocity, or it might even ask you to calculate the final momentum or the change in momentum of m2, okay, how would you go about that? Well, we'd use the principle that of the conservation of momentum. Now, the conservation of momentum, that is always applied to, and it will never not work in a given question. Or I haven't seen them give you a situation where you can't use the idea of the conservation of momentum. Okay, well, the conservation of momentum says that momentum before will equal momentum afterwards. So to start this question, I would state, I thought I had that on there. I would state the conservation of momentum of saying momentum after equals the momentum before. Okay, so you would work out the total momentum before, okay, which is, we know momentum is mass times velocity, so it's m1 times u1, so m1 times u1, m1 u1, plus m2 times u2, m2 u2, okay, is equal to the total momentum before afterwards, which is m1 times v, okay, m1 v, plus m2 v, because they're going to be travelling at the same velocity, because we came up with this idea of a totally inelastic collision. Okay, now, how do we work out this velocity? Well, obviously, all of this looks like it's unknown. That's only because I've just come up with this. I couldn't be bothered putting numbers to it. This m1u1 and this m2u2, you'd be able to work that out because you'd know what m1 is, you know what u1 is, you know what m2 is, and u2. Just in this hypothetical question. But here, we've got two unknowns, okay? We've got m1 that we know, times v, which we don't know, and m2 times v, which again we don't know. But these two, because they're moving at the same velocity, they will have the same velocity, so we can take v out as a common factor because it will be the same. Okay, so it will be v brackets m1, m2. Okay, you know what m1, m2 is, so you just rearrange that to get v. Okay, so v would be all of that, okay, divided by m1 plus m2. Okay, so you could therefore say, now you couldn't take u as a common factor here because they've got different initial velocities, we're assuming. Okay, otherwise, if they had the same velocity, there wouldn't be a collision in the first place unless they were originally moving together at the start. Okay, in other words, they wouldn't collide. So these two would have to be different. Okay, right. So you would give you a velocity for v, whatever that might be. Okay, and then if it asked you to work out the magnitude of the impulse exerted on A by B, all you have to do is work out the change in momentum of A or the change in momentum of B. It should be the same. Okay, so that's what you would do there. So very, very quick overview of that. Right, now kind of the key thing of what I wanted to do in this video. So that's really quite kind of easy stuff. And again, well, all momentum I would say is quite easy. Okay, so there's one more thing actually I want to just go through with you. So we know that there's this thing that you obviously have to be aware of. That the resultant force is equal to the change in momentum, okay, in other words the impulse over the change in time. So it's the rate of change of momentum or the rate of change of impulse. Yeah, the rate of change of momentum, okay, is equal to the resultant force. But how do we come to that conclusion apart from the fact I've just told it you? Which doesn't really say how we've come to it in the first place anyway, but the idea stands. Now, what do we know is the resultant force? Well, quite clearly it starts with F equals ma. But how do we get from F equals ma to what we've got on the board there? Now, obviously we can't change the mass, that's constant, and we can't change anything to do with the force because we want it in terms of the force. Okay? There's no equation we can get for the mass. Now you could say, well, we do know that W equals mg, okay, so you could rearrange that to get the mass. But again, that's not going to get us anywhere, because if we put the mass is equal to the weight over the acceleration due to gravity into this equation, well, that's not going to help us at all. Okay, so it has to be something else. Now, this acceleration is obviously what we're going to focus on. Now, it comes from, now I could just simply state the equation that we're going to put into it, but I just want to build it up. Now, you know the Suvat equation, V equals U plus AT. We take U away from both sides and divide both sides by T. Okay, so we get V take U over T, and that's equal to the acceleration. Okay, so we put that in to, because that's equal to the acceleration, and we've got F equals ma, we put this, it's the same as saying the acceleration, so we put it into the equation. So instead of saying F equals ma, it's F equals m times V take U all over T. Okay, and then what I'm going to do is expand this out. So F is equal to mv take mu over T. Now, this mv take mu, okay, is, well, this mv is the final momentum, and this mu is the initial momentum. So what we've got here is the change in momentum, in other words, the impulse. Okay, so therefore, we can write it as what we've got up here. It's exactly the same now, okay? So, the resultant force is equal to the rate of change in momentum, or the change in momentum, over the change in time. Okay, and obviously you can use that to work out one of the crucial things they may ask you. They may give you a force against time graph, so force on the y-axis and time on the x-axis, and it might be something like this. Okay, say it's at a given, applying a given force, and then it just stops at a given time. Okay, and the area under this is how we work it out. Well, we do the height times the length. Okay, in other words, the force times the time. I know the force times change in time is equal to the change in momentum. So this area represents the change in momentum. In other words, we know the change in momentum is the same as saying the impulse. So therefore, the area under this represents the impulse. Okay. So hopefully that makes a bit of sense to you. Right, that's really all there is to do with momentum. I'm sorry I've kind of rushed through it. I didn't want to make the video too long because I think momentum is easy. It's one of them videos that you just simply need to be able to, one of them topics that you just need to be able to, yes I know this, yes I know this, yes I know this. They're not going to manipulate it in any other way. They're the type of questions you're likely to get asked. Now, quite commonly they will ask about the area underneath, or they will ask about elastic and inelastic, or they will ask about, it's not very good this, yeah, they will ask about is momentum, or what's conserved in a collision. Okay, but really, I don't think they'll ask you to build up to that, but they might do, and I don't see why they wouldn't, okay, because it's all AS knowledge, okay, and obviously A2 as well, if you're doing it as your A2 course, like I am. Okay, so thanks for watching, hopefully it's been helpful, and we'll see you in the next video.